It's time for another math easy solution. I'm going to discuss, further into indefinite integrals and basically this time do some examples on it. And also I have this table of integrals which would be useful when I'm going through the examples, so I can just look up these whenever there's specific integrals I need to find. Okay, so now the first example here, this one just states basically find the most general indefinite integral of this integral here, integral of 10x4 minus 2 secant squared x dx here. So the first thing to do is break this apart using our indefinite integral rules or just definite integral rules. Just break this apart so that we could write it in forms that are like this, so we could actually solve the integral. So this could be written as well. Basically, we could separate these two integrals into two of them, and then we could take the constants out. So this will be x4 minus, this is going to be 2 secant, this one dx, secant squared x dx. Also, always put a dx there, just to have the correct notation for integral. So now we could solve these ones here. The antiderivative, so we just find antiderivative of this one, of both of them. So in this case, the x4, this was just going to be x5 over 5 here, because if you take the derivative of this will be just x4 using power rule. So then minus this one here, the integral of secant squared x using this table. You'll see the proof in this in the video link below is this right here, tan x plus c. So we're gonna get now 2 tan x, and then we always have to add a constant here because we're asked to find the most general indefinite integral here. So this one, we could simplify this further by just basically dividing out this 5 to 10 there. So then we're going to get 2x5 minus 2 tan x plus c here. Now, you can also double check your work by taking the derivative. So if you double check derivative, this one here, you can see this goes down. So we're going to get 10x4 minus 2 secant squared x. That's what the derivative of tan x is. So we get this. And that's exactly this one here, so we are correct. And also I've graphed out this 2x to the 5 with different constants here. So this one's a plus 1, the first one's with a constant of 0. So as you can see in this case, the 0 is, it's 0 at the y and x intersect right there. And then then the 1s will just serve as the y-intercepts here. So this plus 1, this is the red, it's the same function, plus 1, the other one's going to be a minus 1 here. As you can see, they're just different translations of it, and this is just different. So that in this case, the constant is just the y-intercept here. So that's how it look like. So now if we move on to example 2, this one's a bit more complicated looking. This one just the integral of cosine divided by sine squared here, and we're using theta instead of x as the variable here. It doesn't matter which one you use. So basically in this case, it's right now it's hard to see what the indefinite integral is, but if you use some trigonometry and then you just play around with these, you could write this as, well, the sine squared, you could write it as basically sine theta times it by sine theta here. And then if we write the cosine on this side, I'm just trying to rewrite it so it's a form that we have inside the indefinite integrals table above. So we could write this as this. This is a pretty interesting one here. So now this one, you could write this one, is just going to be integral of cosecant using, this is just a definition of cosecant theta here. And this one here is just 1 over tangent or cotangent here. So this is cot theta here, d theta here. So then if you scroll up to the table, we get this one right here. I should do a proof later in another video. I'll do a proof. So basically this integral, that's what we got it in the form of, is just equals to negative cosecant x, and that's what I'm writing here. So that's the indefinite integral is just gonna be negative cosecant theta plus c. And remember, cosecant is just gonna be 1 over sine. Okay, so now if we move on to example 3, this one is actually evaluating the definite integral here, which is from 0 to 3 here, of this integral of x cubed minus 6x here. So we could break this apart, just take the antiderivative of both of these, and you could write this one as, recall from my other videos, basically this one, just find antiderivative of the x cubed, is just going to be x4 over 4 minus the antiderivative. This one's going to be x squared, we put a 2 and then divided by a 2 here, 6. And then this is, you usually write it like this from 0 to 3 here. So what this means is you're going to have to put 3 inside here, subtracted by 0 here. And before I get that, I just want to simplify this first, just divide these out. So I have something like this. So this means we just put the 3 in here, 3 squared, 4 minus, this is going to be 3 times 3 squared, all minus it by, well, put 0 in here. 0, it's going to be 0 minus 0, etc. So this is just 0. So we just look at this value here. This is going to be, well, actually I made a mistake here. This is a 4 here. There's a 4, not a square. So then 3 to the 4 is going to be, yeah, 3 to 4 is actually 81. So then divided by 4 minus 3 times 9. And this is just be minus 27 here. So if you're in a calculus exam and stuff and you don't have a calculator, you can just leave it as that. Or if you plug in the calculator, you're going to get negative 6.75 here. So either one is correct. So now let's do one more, a couple more examples actually. Example 4, this is just another definite integral from 0 to 2 of this one here. So if we just do the antiderivatives of each single one separately and put in our little brackets like this, like above example. So we're going to get, this one's going to be x4 divided by 4. Put a 2 there. This is going to be now x squared. 6 divided by 2, and then plus here this one is going to be 3. Then if we look at this, this is 1 divided by x squared plus 1. If we look at it, this one right here, this one right here, x squared plus 1, that's the one we just have right there, and that's going to be a tan or inverse tan of x here. So we could just write that here as inverse tan of x. So we have this, from 0 to 2 here. So if we plug this in again, we're gonna get, again, if we plug in the 2's inside, we're gonna get this side here when we plug in the 2's. I've simplified this one as just divided by 2. That's what it is, 2, and this one's a 3. And just put in the 2's inside here, and then minus, when you put a 0 here, we're gonna get 0, 0, and also inverse tan of 1, of 0, inverse tan of 0 is also 0 here. So we just divided by, or minus by 0. Simplify this, we're going to get, so if we simplify this, this is just going to be, well, 2 to the 4 minus, this is the same as 2 to 3, because you have it divided by 2, and this equals to 8. So we're going to go 8 minus, this is 3 times 4, is 12, so 8 minus 12 plus, plus 3 inverse tan of 2 here. And this simplifies it to negative 4, negative 4 plus 3 inverse tan of 2 here. So if I try plugging that value in the calculator here, so if you just put negative 4 plus 3 arctan 2, this, you're not going to get an answer with Google. That's because arctangent, remember, this one is the inverse, so it gives you what's inside the tan function, which is in radians by default. So you would have to put negative 4 rad here in the calculator here. So now you're gonna, because it has units here, so the value of arctan is actually in radians or degrees. So then we're gonna get this value here, negative 0.678. And I'll write it down here. So we got this this value here, and this negative just means number, because this is just the net area under the curve. So if you have something like this, all you're doing is add. This is gonna be a negative area. It's gonna be plus. It's gonna be a plus. All you're doing is summing up the areas under the integral, and in this case it has more of a negative one, that's why it's negative. Okay, so now last example today is just this one here, integral from 1 to 9 of this big giant integral here. So basically, what first thing to do here, we could get rid of all this denominator here by dividing this out by every single one here. So we're going to get equals to 1 9 simplified further, this is going to be 2 plus, well, this is just square root t, or t1 over 2, just put it like that because it's easier to take the antiderivative, and then minus, well, this is going to be just, well, t negative 2 here. Let's put a negative there just because it's easier getting the antiderivative of this one here. So just now we have this integral, and then if we write this again out like before, put a bracket, we're going to do that 1 to 9 definite integral method above. So now we're going to, this one, antiderivative of the 2 is going to be 2t, antiderivative of this one is going to be, well, we have to add 2 over 2 here, so this is going to be plus t 3 over 2, and always number divided by whatever this one is, so 3 over 2, so we divide it by that. And this one's going to be, we always add 1 to the top, so it's going to be t negative 1 divided by negative 1 here. And this is the antiderivative. You could just test this by, if you take derivative of this one here, using the power rule, the negative 1 goes down, cancels with this, and it's going to be negative 2. And the same with this one here, this goes down, cancels, you subtract, then you subtract 1 power, so it's going to be 1 over 2. So now we have this value here. So then if we basically put these values in, we're going to have this entire thing all but with t equals to 9 subtracted by where t is equal to 1 here. So put a 9's in here, we're going to get something like this, minus or plus this, the 3 over 2, just you could put the 2 up top here, so 2 over 3. And this is just going to, this negative just becomes positive, so plus, and then it's going to be power negative 1, so 1 over 9. And then when we plug in the ones doesn't really affect anything. This is just going to be a 2 plus 2 over 3. This doesn't do anything. And then this is also going to be plus 1 here, because 1 divided by 1 is just 1. So we get this one here, simplify this, we're going to get 18 in this one, plus This one here, we're gonna get, well, yeah, you could write down this 9. So we could write down, yeah, this 9 to the power of 3 over 2. You could write this as basically 9 1 over 2 to the power of 3, and this is just going to be, well, 3 here. So this is just going to be, because 9 square root, just going to be 3 to the power of 3 is equal to 27 here. So if we plug that in here, so 27 divided by 3 is equal to, well, just 9. 9 times 2 is 18 here. So this is going to be plus 18, then plus 1 over 9, then subtract this by whatever this one here is. Yeah, or just put the negatives out in every single one. So we have something like this. So now we just have to deal with algebra here. So if we add these two up here, this is going to be, well, 36. And then this negative 2 and negative 3, that's just going to be, well, negative 3 subtracted. We're going to get 33 plus 1 over 9 minus this left over, just 2 over 3 here, just times the top and bottom by denominator. You could put in a calculator or whatnot, or if you don't, because you could, if you're in an exam, you could just leave it like this and that'll be your answer. But if you want to simplify it, just work on your algebra. Times by 3 over 3 to common denominator. We're going to get now, so this part's going to be 1 over 9. Subtract this by, this is going to be 6 over 9 here. This equals 2, well, this is going to be negative 5 over 9. Yeah, thus we get equals to 33 minus 5 over 9. You could even write this in a fraction form. Yeah, so when we get this, you could write this as a fraction of, basically, of this 1 over 9 factor here. Is basically by, you go 32 plus, let's go 9 over 9 here, minus 5 over 9, because this just equals to 1, so we're just breaking that apart. So then now this is going to be 4 over 9 here. So then the answer, you could write it as, I'm just doing this a bit extra here. This is just going to be 4 over 9 here. Or this could be written as 32 and 4/9. So this is a fraction notation here. And 32 and 4/9, that's this, all it means is this right here. And this could be considered as the decimal place here. So that's all for today. Hopefully you learned from these examples here, and also a bit of algebra here. But that's all for today, and yeah, so yeah, that's all for now. Remember, you can also download these notes in the Dropbox link below, and that's all for you learned about these useful examples here. And then stay tuned for another math easy solution.